Hello, so welcome to the first colloquium of 2014. I believe it's the first one. I just came here myself, so I don't know if you had last Monday. I don't think so. So we actually very happy to have an amazing speaker today, George Zweig, whose career spanned the last 50 years or so, and he received his bachelor's in math actually from Michigan in 1959, before many people in this room were born, and then PhD in physics from Caltech in 1963, after which he went to CERN as a CERN fellow, or equivalent of what it used to be back then, and there he made his seminal work on understanding of the building species of mesons and baryons, which are now known as quarks, but George called them aces, and today in his colloquium he will tell you all about aces. And then he switched fields rather abruptly and became a biologist, and actually learned many things about human ear and hearing. And one of the puzzles he solved in the 80s was why some people hear this persistent ringing in their ears and how to cope with it. And then he worked at the Los Alamos National Lab from 81 to 2003. And then he made another career swing and went to Renaissance hedge fund and worked as a hedge fund manager for 7 years or so. And then in 2010, he was fed up making money and decided to go back to science. And he's now at MIT Research Electronics Lab. And today, George is going to tell us about his contributions to the Quark model, how it all started. So please welcome George Zweig.
Okay, that should work. Well, this is the 50th anniversary of the discovery of quarks, and last year was the 40th anniversary of the invention of QCD. QCD really developed in two phases. First was the discovery of quarks, and then there was the question of the specification of their interactions, and we're going to really talk about the first part, the discovery of quarks. These two different areas really came from two different kinds of thinking. That of Rutherford and Bohr, related to the discovery, and that of Einstein, relating to the invention of QCD. And the story really begins with Henri Becquerel in 1896. Becquerel was trained both as an engineer and as a physicist. At the time, in 1896, he was head of the Highway and Bridge Department in France, but he had an interest in physics, and in particular, the phenomena of phosphorescence, where you would shine light on a substance, and then it would emit light back at you at a different frequency. And at the end of 1985, Röntgen discovered X-rays, and Becquerel started to wonder whether or not phosphorescent substances would emit X-rays. And he was especially interested in the uranium compounds. And so he took these uranium crystals, exposed them to bright sunlight, wrapped them, wrapped photographic plates in black paper, and then put these substances against the photographic plate to see if an image would emerge. And in fact, it did. And he thought that X-rays were emitted in phosphorescence as other forms of radiation were. But once, when the sun was not so bright, and he didn't think it was worthwhile exposing it to the sunlight, he put this uranium crystal in a drawer together with a photographic plate. And when he developed the photographic plate, he saw an image, somewhat like the image that you see here that he took later on. How do I get this to point a light? The red dot. The red dot does it. So here is one of his later images. You can see a Maltese cross here, something that he put between the uranium crystal and the photographic plate. And so he came to the conclusion, the fact that there was another form of radiation that was being emitted by these uranium crystals. Rutherford, who was at Cambridge in 1899, showed that in fact there were two forms of radiation that were emitted that he called alpha and beta. He then worked, he then left England and went to Canada and worked in Montreal at McGill. And there he teamed up with a young student, Frederick Soddy, and in 1903 they proposed what was called the disintegration theory of radioactivity. In other words, they showed that it was an atomic or a subatomic phenomena, and it was not a molecular process. And Rutherford received a Nobel Prize in chemistry in 1908. Frederick Soddy also received a Nobel Prize in 1921, also in chemistry, but for entirely different work. And in fact, there were 11 of Rutherford's collaborators, students, and people that worked in his labs that got the Nobel Prize. You see here 2 years later, in 1910, Rutherford sitting in the middle of a group here in a group photograph. Now, things really got interesting when a postdoc came from Germany to work in Rutherford's lab. This was in 1909, and he teamed up with a young undergrad, Ernest Soddy. Undergrads could do things. And they started to study the scattering of alpha particles off of thin metal plates. They wanted to see what happens when this radiation bumps into metal. And as it says here, they say, a conclusive evidence was found of the existence of a diffuse reflection of the alpha particles. A small fraction of the alpha particles falling upon a metal plate have their directions changed to such an extent that they emerge again at the site of incidence. Well, this was a totally unexpected discovery, and it was properly interpreted 2 years later by Rutherford, who said that the only way they could understand these dramatic backscatterings that they were seeing was through a separation of charge in the nucleus. And this scattering was really taking place then from concentrated point charges. And there was a charge separation in the nucleus, which of course was impossible, because if the two charges that were separated were static, well, then they would be pulled together. And if they weren't static and one rotating about the other, then they would emit like tiny antennae, and they would spiral also back together. Ernest Marsden, this 20-year-old here in 1909, in 1914, showed that the nucleus, that the center of charge, in fact, was not a single charge, but it was many charges, contained many protons. And then the problem was, well, why didn't this thing explode? So it was a totally incomprehensible situation, and one which Niels Bohr, was very interested in. He got his degree in either 1911 or 1912. In 1912, he went to see J.J. Thomson because he was interested in electrons, and J.J. Thomson's place was the place you go if you were going to study electrons. But Thomson was totally uninterested in Bohr, and when Bohr went to visit Rutherford's lab, he found it very exciting. He stayed there several months. He then returned from 1914 to 1916, and he combined this idea of charge separation, which was incomprehensible, with Planck's idea of the quantization of radiation to postulate this idea which we call stationary states, where a light is emitted as electrons move from one state to the other. And this wasn't straightened out, an understanding of this, until 1925, when Heisenberg and Schrödinger, but especially Heisenberg, developed the theory of quantum mechanics, which proved to be also a way of thinking, at least in the case of Heisenberg. Heisenberg said you would have avoided all this problem and confusion in the past if you would have only worked with observables. And he formulated his quantum mechanics in terms of a matrix of these spectral lines, and the rules that these matrices would observe. And later on in 1943 and 1944, he published 2 papers where he said that the physics of the current time, which involved scattering, should really be dealt with in terms of scattering matrices, also organized into these matrices called S matrices. So his contribution was also one that dealt with how you should do physics as well as a particular law of physics. Well, my first introduction to physics came in 1947. I was 10 years old. I always, after school, would listen to one of my favorite radio programs, The Lone Ranger. And one day, the announcer said that if I would send in 15 cents and a box top from the Kix breakfast cereal, I could receive an atomic bomb ring. This was 2 years after the atomic bomb had been dropped on Hiroshima. I decided I would get one of these. I talked my mother into getting Kix breakfast cereal, and by return mail, in fact, I received the atomic bomb ring as you see over here. And if you would take it into a dark room, and I would always take it into the closet because in the daytime that's where it was dark, and you'd wait until your eyes would acclimate, and you'd look down the axis of this ring. You see, after you've taken off the cap, look down right here, you'd see these incredibly brilliant flashes of light. There was a radioactive source of polonium in here. And the polonium would emit these alpha particles, and they would hit a zinc sulfide screen, which is in here, which is exactly the same kind of screen that Marsden and Geiger used in their experiment. I was so fascinated by this that I sent away for a second ring, not knowing that the half-life of polonium was 138 days. But in any case, this made a big impression on me. Well, the same year, 1947, the pi meson was discovered, as well as the K meson. The pi meson was expected as the carrier of the nuclear force, but no one ordered the K meson. No one knew why that was around. And 2 years after that, a paper appeared in the Physical Review, a very interesting paper by Fermi and Yang, titled Armazones, Elementary Particles. And I wanted to read from that paper. Let me see if I can see it here. They say, right here in the introduction, in recent years, several new particles have been discovered which are currently assumed to be elementary. That is, essentially structureless. The probability that all such particles should be really elementary becomes less and less as their number increases. And then they go on here and say the hypothesis that pi mesons may be composite particles. You know what? You're going to have to excuse me so I can read this. Yeah, the hypothesis that pi mesons may be composite particles formed by the association of a nucleon with an antinucleon is discussed. From an extremely crude discussion of the model, it appears that such a meson would have, in most respects, properties similar to those of the meson of the Yukawa theory. But these were actually honest men. And so they point to a problem. They say, right here at the bottom of the page, unfortunately, we have not succeeded in working out a satisfactory relativistically invariant theory of nucleons among which such attractive forces act. This problem of making a pion out of existing particles was to haunt elementary particle physics later on, both in terms of what was later on called the Cicada model, where the lambda particle was added to the proton and neutron as the fundamental particles, and then also the Bootstrap, where people, as we'll see in a moment, would try to use the existence of they would try to use the existing particles to bootstrap themselves through their mutual interactions. Well, 10 years later, in 1957, that is 10 years after I looked at the atomic bomb ring, I was an undergraduate at the University of Michigan, and quite by accident, I found this Scientific American article written by Murray Gell-Mann and E.P. Rosenbaum. Rosenbaum was one of the editors of Scientific American. It was called Elementary Particles. And they list the elementary particles. And there were 19 in number. This was a rewrite of a paper that Murray Gell-Mann and Art Rosenfeld wrote in the Annual Review of Nuclear Sciences, also in 1957. And the particles that were listed there were first the point particles. These were all elementary. The 3 leptons and the photon. And then the extended particles, the spin-a-half baryons, and there were 7 that had been found at that time, and an 8th one was thought to exist, and 7 mesons. There was no thought that there would be an 8th meson. Now, in the very same Annual Review of Nuclear Sciences where these tables were published, there was another paper, a review paper by Sam Lindenbaum talking about resonances. And here we have the graph of the total cross sections in hydrogen of pi plus and pi minus p, and you can see the resonance here, and then there's a, oh, somehow I'm running out of power. There we go. And some sign of resonance is here. So you had sort of side by side in journals, the elementary particles and the resonances, and side by side in the minds of the theorists, these 2 classes of objects that had absolutely nothing to do with one another. Well, I went to Caltech in 1959. Let me try to make this one smidgen small. Caltech was a small place, small physics department. Its chairman was Carl Anderson. Carl had discovered the positron, he discovered the muon, and he presided over a very young and vigorous department. Small but vigorous and smart. There were 6 people at the department at that time that went on to win the Nobel Prize. It was an interesting place. It was very dynamic. And I thought I'd give you a little taste of the place by describing what happened at one of their theory seminars, which was not that unusual, actually. Every Tuesday at 2 o'clock, the theoretical physics seminar would take place. It was in a small room. And Gell-Mann and Feynman would walk in and sit in the middle, front row center. And everybody else would come on in and sit behind them. After the speaker was introduced on this occasion, there was Marshall Baker, a well-respected physicist. Marshall started to talk, and as he started to talk, Murray started to reach down and get his New York Times. And then, boom, he'd open the New York Times. So 1 foot in front of him like this was Marshall Baker, and then there was Murray, and then there was the New York Times between them. And about a minute or 2 into the talk, Feynman would sort of lean over in his best Far Rockaway accent. He would whisper, "Is this guy smart?" He was whispering was loud enough so everybody, including Marshall, could hear the question. But only everybody but Marshall could hear the answer. And the answer was given this way. If Murray thought the guy was smart, he would go like this. And if he did that, then Feynman would ask questions. If he go like this, Feynman would shut up. So on this occasion, Murray goes like this. Of course, Marshall has no idea what Murray says, and Feynman starts asking. Now, everybody knew the answer to the question, but what we didn't know was that Marshall Baker stuttered. And the more stress he felt, the worse his stuttering got. And as the questioning proceeded, the stuttering took longer and longer. And at one point, he went into an infinite loop. And at that point, Feynman slams his hand down on one of these paddles and says, "God damn it, I can't get our answer out of this guy." And he gets up and he walks out. Well, When I went to Caltech, I didn't know if I was really smart enough to be a theorist, whether I could cut it. And experiences like this in that seminar room didn't help any. But before I attended this seminar, after my first year at Caltech, when I still thought I might want to be a theorist, I went in to see my quantum mechanics professor, Bob Christie, to ask him if I could work on a problem over the summer. And Bob looks at me somewhat contemptuously and he says, "You know nothing. Why don't you go over to the synchrotron and learn experimental physics? If you become a theorist later on, it'll do you some good, and you won't have time to learn it later anyways." So I actually went to see another professor, H.P. Robertson, who taught general relativity. And I asked him about a problem. And he said general relativity is dead. He says, but if you insist, you can read Singh's book on general relativity. Come in and we can talk about it. So at that point, I went over to the synchrotron and I met Alvin Tallestrup. And Alvin was going to run an experiment at Berkeley, the first users group experiment. He was going to study what was called the delta I equal half rule. He was going to look at the reaction K plus goes to pi plus pi 0 plus gamma. And I thought you could piggyback off of that experiment, use the Ks to measure this decay K mu 3, K plus goes to pi 0, mu plus neutrino. And if you measure the polarization of the mu out of the plane of decay, you could see if time reversal symmetry held. Parity violation had just been discovered a few years earlier, and I thought it might be good to see if CP violation also existed. So that was going to be my thesis experiment. And I worked on it very hard for 2 years. We went and we ran the experiment. It was rather difficult, interesting story in itself. Came back with a few 100,000 photographs, and I started to scan, and I didn't find an effect. And this was very, very disappointing. So what I had ahead of me was at least 2 years of careful analysis to measure the errors and establish an accurate upper bound, and I didn't want to do it. So I went to Mexico, camping, to the Yucatan Peninsula, to think it over. And when I came back, I decided I'd switch to theory. That was the lesser of evils. So I went in to see Murray and I asked him if he would be my thesis advisor. And he was a natural guy because I had seen him on a few occasions before talking to him about Alvin's K decay experiment and K decays in general. And he had a lot of students, and the students got out early. So when I asked Murray, he sort of paused and he said no. He was going on sabbatical to the East Coast, but he would talk to Dick. Dick was Richard Feynman. And I would have never, had the guts to go in and talk to him or ask him to be his thesis advisor. But I felt that since Murray was going to talk to him, I'd have to go in and see him. So I went in about a week later, and I asked him, and he looks at me and he says, Murray says you're okay, so you must be okay. Why don't you come in? Why don't you come in every Thursday at 1:30, and from 1:30 until 4:15 we'll talk physics, and 4:15 we'll adjourn for tea and go to the colloquium. And so that's what we did, and I'd go in every Thursday. And the week before my meeting, I would work like crazy because I didn't want to bore the man. And we essentially covered all of physics. We covered theoretical physics, as it was known at that time. There was one branch called axiomatic field theory, which was practiced by Whiteman and others at Princeton, and Feynman hated it. There was something that I called theory related to belief, which was practiced by Jeffrey Chu at Berkeley. And I have a quote here from Chu in 1961, where he says, I believe the conventional association of fields with strongly interacting particles to be empty. Field theory, like an old soldier, is destined not to die, but just fade away. There was theory related to experiment, which was by far the most interesting. There was theory related to particle classification, where there was no dynamics, and the groups G2 and SU3 were in contention. Murray, as well as Li and Yang, thought that the particles should be classified according to representations of G2. Murray realized that that wasn't right and switched to SU3, but Li and Yang just continued with G2, and it was some question of who was right. It was rather interesting and exciting. Then there was dynamics, which really had nothing to do with classification, and that involved what was called the bootstrap, which was a very beautiful idea. And there was a wonderful paper written by Fred Zachariasen, who is a faculty member at Caltech, where he bootstrapped the row meson. And what that meant was the following. If you start off with 2 pi's, and you put them in the spin parity 1+ state, so you scatter them off one another, and they have that angular momentum and parity. If the force between them is created by the exchange of a particle that has the same quantum numbers as the channel you're looking into, in this case that would be a particle called the rho, then you would find that the force would be attractive. And you'd find that it could be so attractive that it in fact would create a resonance in pi-pi scattering. And then if you said, look, the particle that's being exchanged is the same particle that's formed in the resonance, you have an equation. And you can use that equation to compute the mass and the coupling constants, and it's roughly right. And so that was the idea of the bootstrap. And that was, I think, by far the most popular theory of the time. But what you couldn't bootstrap, and what the bootstrap people never mentioned, was that you couldn't bootstrap the pion out of a nucleon and an antinucleon, like Fermi and Yang had tried to do. Well, there was a lot of stuff going on in experimental physics. Since the 1957 paper, there was a new point particle. There were now 4 leptons that were known. With respect to the extended particles, they found the expected 8th baryon, this thing psi 0, but they found an 8th meson. And then they found many, many resonances. And in fact, in the Reviews of Modern Physics in April of 1963, you have 26 meson resonances that are listed. Well, one Thursday afternoon, I went in to see Feynman, and I wanted to talk to him about another resonance. This wasn't interesting because there were lots of resonances. But what was interesting was the way in which this particle decayed and what it didn't do. You see over here a Dalitz plot for the reaction. So you have the invariant mass, the K, well, let me tell you what the reaction is. The reaction is K minus P goes to lambda plus K bar. And here you see the Dalitz plot for the reaction, and then the projection down here on the invariant mass of the KK bar system, where you see this big peak. So there's a resonance. There's no question about it. It's a little funny. It's right next to the edge of phase space, but that's fine. That should just sort of hinder the decay, but it should not eliminate it. What was amazing was the fact that it didn't look like it was decaying into a rho plus a pi. If it decayed into a rho plus a pi, the rho would then decay into 2 pi's. And so you should see a bump in the 3 pi invariant mass. But when you plot that, you get really no statistical peak. And if you try to do an order of magnitude calculation of the branching ratio, it goes like the momenta of the particles in the final state cubed. You find that you would expect that you get 4 times as many rho pi's as KK bars. And in fact, the ratio goes the other way. You get 35 times, at least 35 times as many as KK bars. Now, the authors of this paper note that there's a problem. They say the observed rate is lower than predicted values by 1 order of magnitude. However, the above estimates are uncertain by at least this amount, so that this discrepancy need not be disconcerting. Well, they got the order of magnitude wrong. It's suppressed by 2 orders of magnitude. And it was enormously disconcerting, because I had learned from Feynman that in hadronic physics, everything that possibly can happen does, and with a maximum strength allowed by unitarity. And here you had a suppression of 2 orders of magnitude. The only way you could get that is through some kind of symmetry, and there was no symmetry present. Feynman just thought the experiments were wrong. And he went into a big tirade about how when he proposed V minus A theory, all the experiments were against him, and then all the experiments ended up being wrong. And he was right to really resist this, because it was absolutely bizarre. If you looked at it, it just shouldn't happen. Well, I just couldn't leave this thing alone, and in the end, the way that I resolved the problem was to think that hadrons, mesons, and baryons had constituents that I called aces. There were 3 of them. Oops, excuse me. There were 3 of them, as you can see up here. A nucleon-like objects called P0 and N0, and another object called lambda 0. And I assigned to each particle a ace and an anti-ace. So the rho, like the pion, would be made out of these 2 nucleon-like aces, and the phi would be made out of this lambda 0 and the lambda 0 bar, and the k star would have one of these lambda 0s and then maybe an n0 bar. And then there was a rule for decay. So I said that in decay, aces are conserved. So that if you start off with a particle, an ace and an anti-ace, and they go like this, and they start to move apart, that's going to polarize the vacuum. And then out of the vacuum, a pair is going to pop. And then the objects from the pair would then match up with the aces in the original state, and you would get a decay that would go like this. This is sort of in modern notation. I had a Tinker Toy view of this in the paper at CERN. So, since the pi or the rho is just made out of these N0 type aces, and the phi is just made out of the lambda 0 type aces, this decay couldn't occur. Now that in itself, that's one input, one output. But the thing that really clinched the deal were the masses of the objects. So I had a rule for meson masses. I said that the masses were the sum of the constituent masses plus the energies of the interaction, minus the binding energies. And that the differences in masses between the aces was a lot larger than the differences in any of their binding energies. And if you assumed that, then you got the following. If all the binding energies were the same, you would get the mass of the rho was the same as the mass of the omega, and they approximately were, as you can see up here. And the k star would be heavier than either the rho or the omega, and the phi, which had the most lambda zeros, would be the heaviest of all. And if the binding energies would average out, so you'd average the binding energy of the lambda with the lambda 0, and the binding energy of the nucleon-like ace with the antinucleon-like ace, if you could average that, then you would get this mass relation. Mass squared of the phi is twice the mass squared of the k star minus the mass squared of the rho. And that relationship worked remarkably well. So you were killing 2 birds with 1 stone. Now there was also a problem of what you do with the baryons. And I noticed that if you use 3 aces to make a baryon rather than 2 aces and an anti-ace, if you use 3 aces, then the particles would fall in representations of 1/8s and 10s. And that's exactly what was observed. Now if you use 3 aces, they had to have a baryon number of 1/3. And if you use the Gell-Mann-Nishijima mass formula with B equal 1/3, you get these fractionally charges for the aces. Well, the idea was that aces, not hadrons, interact. So, for example, if you wanted to know what the pion-nucleon coupling constant was, what you would do is think of these aces here. I've dropped the subscripts to just simplify the notation. These are the aces. You'd have 2 of them going over here and 1 of them going over here with the polarization of the vacuum. But you could do this 2 ways. In the wave function of the proton, for aces, you'd have to anti-symmetrize 2 of them. And this antisymmetric pair could end up here, or it could split. So you had 2 degrees of freedom, and that corresponded to the F couplings and the D couplings. This, by the way, was called Zweig's rule, which is different than the OZI rule. The OZI rule tells you what's forbidden. This tells you what's allowed and by how much. But also, when a hadron would undergo electromagnetic or weak interactions, it would be their aces that interact. So when a neutron decayed, it wasn't the neutron that was decaying, it was the N0 in the neutron that was decaying. So the electromagnetic and weak currents were made out of these aces. So this is a little bit like what now people call the current quark model. Well, more specifically, hadrons had point constituents. These were the aces. Now, the other point constituents were the leptons. So the idea was that there should be a one-to-one correspondence between the point constituents for the hadrons and the leptons. And at the time, 4 leptons were known, so I thought there should be 4 aces, although only 3 were observed. That's why I called them aces. And in retrospect, I might have called them dice. But in any case, that's where the name comes from. So this provided some understanding of the origin of SU3 symmetry, but it went way beyond SU3 symmetry because it restricted the representations that you could have in SU3 and also their quantum numbers. So the baryons that came only in 1/8 and 10s, the mesons only in 1 and 8s, or the 1 and 8s could mix and you could get 9, like the vector mesons. The lowest lying states would involve no angular momentum, and so you would get a 1/2 plus octet, and that was observed, and a 3/2 plus decaplet, and that was observed. And for the mesons, you, again, with L equals 0, get the pseudoscalar mesons and the vector mesons, and that was observed. So all that worked. But then you also had these orbital excitations with L equal 1 and L equal 2 and so on, and there was evidence for those states. And also, very interestingly, certain spins and parities and charge conjugations couldn't exist. And so we have here this list of forbidden states, and in fact, none of them do exist, and none of them did exist. So the origin of the symmetry breaking was attributed just basically to the masses. So you broke SU3 symmetry by making the lambda 0 heavier than the N0 or the P0, and you would break SU2 symmetry by making the N0 heavier than the P0. So this led to a lot of simple rules. For example, for a baryon in a multiplet, the more negative it was, the heavier it was. And that was true for everything. And for example, for mesons, you would say the more lambda zeros it would have, the heavier it was, like the phi and the rho and the k star, and that was also true. By the way, these mesons were called deuces, and these objects, this is from the CERN paper, and these objects were called trays, and this represents the wave function of a proton in certain terms of its aces. And you didn't have to know anything about SU3 couplings if you wanted to figure out what the coupling constants were. All you had to know is what the wave functions were, and then when a particle decayed, these objects would just flow in every way they can to form whatever it could, and by just seeing all the possible ways it could happen and adding them up, you would get the SU3 coupling constants. Okay, there was a rule for baryon masses, which was exactly the same as for meson masses, except there was no 3-body forces. And I wanted to give you what was my favorite relationship here, which looks at both the SU3 and the SU2 breaking. And what it says is, if you look at the baryon octet and you find the 2 isospin 1/2 states, and you look at their mass splitting, so the neutron-proton mass splitting and the Xi mass splitting, and you sum those, that's the same as the mass splitting in the sigmas. And the masses that you see here, the 7 MeV and 8 MeV, this is the masses that were known at the time. Now we know that The left-hand side is this number, 8.14 plus or minus 0.021, and we have the other side over here. So these two sides now disagree by only, well, you can see it's within experimental errors, but it's a relationship which holds to like 2.5%. So it's an incredible relation. As far as I know, no one's still to this day actually has an explanation for why this works. But this is just an example of the kind of relationships that what you can find. So this is like what they now call the constituent quark model, but one doesn't have to assume any potential. So it's not the naive quark model. Naive quark model assumed some potential and did a calculation, and I really didn't like it because you were assuming something that you knew was wrong, which was a specific form for the potential, and then you didn't get much for it. But from these general considerations, you could find that there were lots of relationships that in fact appeared to hold at least approximately correctly. So there are lots of more relationships, which I'm not going to go through them with you, but I just do want to say that there was some evidence for orbital excitations and mass splittings with L.S couplings. You could also relate mass splittings with fermions to those of mesons, so the fact that lambda was heavier than the neutron or the proton meant that the k star was heavier than the rho or k heavier than the pi, and so on. So there are like 80 pages of ideas and relationships. But I do want to say that this was not as easy as it looks. Of the 26 meson states that were published in the Reviews of Modern Physics, and this was the precursor of the particle data group publications, we now know that 19 don't exist. So out of the 26, 19 don't exist. And of the 19 that don't exist, 7 of them that were listed were ones that you couldn't form out of aces and anti-aces. They were on this list of forbidden states. So you might say, well, how did the guy do this? I mean, what was going on? Well, this is where the training in experimental physics was absolutely crucial, because there were somewhere between 200 or 300 papers. And so I read them all and then just ranked them according to how likely I thought that they were actually right, or how likely it was that they had other evidence that would indicate that the results were correct. And I think once you did that, the conclusion was obvious. It was just that people didn't have the interest or the patience to go through it and actually look at what was there. Well, what did people think? Well, I had a hard time thinking that aces weren't real particles because they had dynamics. I mean, they were conserved in reactions. Particles in the initial state went to the final states. They had angular momentum. They had L.S mass splittings. What would it mean for them not to be real and yet have all these relationships be true? So I applied what they call the duct test. If it walks like a duck and it quacks like a duck and it swims like a duck, it's probably a duck. When I went back to Caltech from CERN, I went into Murray's office and I told him about what I had worked on. And he looked at me after I was finished and he said, "Oh," he says, "the concrete quark model. That's for blockheads." Murray did not like the concrete quark model. He didn't like the idea that these objects were real. In fact, in 1972, which is 5 years after the deep inelastic scattering experiments that were performed at SLAC that led many people to believe that quarks were real, Murray published a series of lectures that I'd like to quote from because they're quite interesting. He says, in these lectures I want to speak about at least 2 interpretations of the concept of quarks for hadrons and the possible relations between them. First, I want to talk about quarks as constituent quarks. These were used especially by G. Zweig. Well, I think it would have been more precise for Murray to say these were introduced by G. Zweig. After all, they weren't like tools lying around in a toolbox that anybody could grab and just use. In any case, Murray goes on and he says the whole idea is that hadrons act as if they were made up of quarks. but the quarks do not have to be real. Well, that's really a mischaracterization of what the idea really was. And then Murray goes on to say there is a second use of quarks, the so-called current quarks, which is quite different from their use as constituent quarks. If quarks are only fictitious, there are certain defects and virtues. The main defect would be that we never experimentally discover real ones, and thus will never have a quarkonics industry. The virtue is that then there are no basic constituents for hadrons. Hadrons act as if they were made up of quarks, but no quarks exist. And therefore, there is no reason for a distinction between the quark and the bootstrap picture. They are just two different descriptions of the same system, like wave mechanics and matrix mechanics. That was Murray's vision, and it was a very beautiful one. Well, what did Feynman think? Well, Feynman had no quarrel with quarks as objects in toy field theories, like the current quarks, or the construction of the electromagnetic and weak currents out of aces. That he thought was fine. But the idea of concrete quarks he really, really disliked. He thought that the correct theory should not allow you to say which particles are elementary. And he also hated Zweig's rule because he thought it was inconsistent with unitarity. Because they said everything should happen that possibly can with a maximum strength. And that rule violated this idea. Well, it was in the May of 1968, and I was walking over to the Caltech cafeteria, the Greasy, and I bumped into Feynman. And he had just gotten back into full spring and high energy physics. He had tried to renormalize gravity, and it didn't work. And he went off and he did other things for a while. But in 1968, he got back into the swing of things, and he had taught a course in elementary particle physics. And he was very excited about it. And he told me all the stuff he covered. And then as we were walking, he stopped and he looked at me and he said, "Did I miss anything, Zweig?" So he knew that he missed something. And so I told him once again for the nth time all about aces. But this time he really listened. He looked at me. And when I finished, he goes like this. He says, "I'll look into it." 3 years later, I bumped into him. He had worked with two graduate students, Mark Kisslinger and Finn Ravindal. And they had looked at the photo production of resonances, some of the experiments having been done at the synchrotron at Caltech, looking for evidence of aces. And as I say, 3 years later, I'm going to my office, and I see him down the hall, and he's coming towards me, and he has this enormous smile on his face. And this time he's not going. This time he's not going like this. He's going like this, and he's walking like this. And he stops. He's like 1 foot in front of me, and he sticks out his hand and he says, "Congratulations, Zweig, you got it right." Well, let me get back to where we are. There were legitimate problems with accepting aces as constituents of hadrons. The first problem was that they violated the spin statistics theorem. That's a problem. You couldn't make the omega minus. You couldn't have 3 lambda zeros all in the same state with their spins aligned, giving the omega minus spin 3 halves. So it was a little bit like Rutherford's atom and Bohr's orbits. They couldn't exist. Current theory said you couldn't exist. I thought somehow it would take care of itself. It was a little bit also like Wegener's continental drift. You know, he thought that the continents drifted apart. North America and South America at one time were together, and then they drifted apart. People didn't believe him. There was overwhelming evidence for it, geological evidence, evidence in the fossil record, but there was no mechanism. It was against current understanding. Also, aces violated current dogma. They weren't consistent with nuclear democracy, and they weren't consistent with this idea that Heisenberg had that you only work with observables. Nobody saw these things. They were just lying around. They got potential interactions with the one. I mean, it looked like you were doing the kinds of things with quantum in the pre-quantum mechanic days that led you into trouble. So it was a little bit like Copernicus's view of solar system. It just wasn't consistent with how people thought. Well, you might ask yourself, what would you have believed if you were alive then? And I think you could have used Bayes' theorem. And you could actually use Bayes' theorem today to evaluate current theories. What you really want to know, or what you would want to know at that time, is what's the probability that ACEs are these real particles given the experimental evidence? And you can write that in this form, a ratio of 1 over 1 plus lambda. Well, lambda, according to Bayes' theorem, is some combination of these probabilities, some conditional and some unconditional. The point is that 2 of these probabilities you sort of know. You know that the a priori probability that ACEs don't exist is pretty high. If you had no experimental evidence and someone told you about ACEs, you'd think, well, this isn't going to be right. So that probability is 1, or close to 1. And the probability that the experiments would exist given that you had ACEs, that's also close to 1. That's how ACEs were cooked up, to make that probability 1. So you know these 2 numbers. So that means that this number lambda is reduced to a ratio of 2 numbers, both of which are small. What is the probability that you could explain the experiments without ACEs? Well, that's pretty hard to do. People tried, no one was able to do it. So that's a small number. And you have to weigh that against the probability that ACEs are these real particles and they're without any kind of evidence whatever. And that's also small. Who would think that that was right if you didn't have evidence? So you would have acceptance when this probability would be a lot less than that. Now, if you're a theorist working in the Einstein tradition, the probability that you could explain the evidence if you didn't have ACEs, you'd think that that was high compared to this probability that they exist in the abstract. After all, you're a theorist. You invent all sorts of theories. You should be able to get that. Whereas if you're in the Bohr-Rutherford tradition, I think the probability would go the other way. Well, when did acceptance come? The first guy that accepted his right was Linus Pauling. This was like 2 or 3 months after I sent my CERN preprint out. I get Gatley proofs from Linus Pauling, college chemistry, where he talks about ACEs. He's got the ACE notation, the whole thing. And he asked if he made any mistakes and if he could go ahead with it the way it was. And he didn't make any mistakes. So he, from a great distance, could see it was obviously right. Dalitz, who was a nuclear physicist, didn't have much trouble with it. He was used to constituents. He just changed constituents. Feynman accepted ACEs when he could see them for themselves, discover it all on his own in a place that no one had ever looked before, which was in photo production. A lot of people accepted it with the deep inelastic scattering experiments at SLAC. And the holdouts, I think, finally came around when the psi and the J were discovered. Very narrow states, and narrow for exactly the same reason that the phi was narrow. It was just a different quark that was involved. Well, a year and a half ago, I was at the Santa Fe Institute. Chris Llewellyn-Smith was giving a talk there. And he was introduced by Jeffrey West. And Jeffrey West noted that Murray and I, both of us were in the audience, had invented ACEs and they were discovered at SLAC. And I corrected Jeffrey. I said, no, we discovered ACEs and our discovery was confirmed at SLAC. And then afterwards, there was some discussion of whether things are inventions or whether they are discoveries. And when I mean, if you look up what these terms mean, if you need to, the invention, as it says in the dictionary, is a product of the imagination. And the discovery is the act of finding or learning something for the first time. So I think current quarks, as is QCD, is really an invention. It's a discovery of the human mind. Whereas concrete quarks, or ACEs, were really discovered just by looking at the data and the Rutherford Bohr tradition. Well, the CERN report in 1964 concludes in the following way, and let me read from the conclusion. There are, however, many unanswered questions. Are ACEs particles? If so, what are their interactions? Do ACEs bind to form only deuces and treys? What is the particle or particles that is responsible for binding ACEs? Why must one work with masses for the baryons and mass squares for the mesons? And more generally, why does so simple a model yield such a good approximation to nature? And in the last sentence, it concludes with, there is also the outside chance that the model is a closer approximation to nature than we may think, and that fractionally charged ACEs abound within us. And indeed they do. Thank you.
Thank you, George, for this historical sketch. And I have time for questions. Leon.
Did any of this give any indication of what's now called asymptotic freedom?
No. No, I thought that there was something that bound ACEs. I don't know if you noticed the pictures that I had of the mesons. There was an ace and an anti-ace, and they're on a spring. So I never drew an ace by itself, because you never saw one. So I actually thought that they were on a spring. And whether the spring would break or not, I had no idea. Now, asymptotic freedom, a spring isn't the right potential, but it binds them. No, but there's absolutely I had no thought of asymptotic freedom.
Just follow up your question. Once you start thinking about spring, did you ask the question whether it will break or not? Or you didn't bother asking that question?
Oh, I bothered asking it, I just couldn't answer it. I didn't know. Furthermore, I was very discouraged because I thought even if I could figure out what the right theory was, I would never know if it was right because it would be so nonlinear I couldn't calculate with it. So that was very discouraging.
Other questions?
There was some indication that there was like a delta function potential that was present. So but you know, you always want a lot more outputs than inputs. And it was hard to go beyond what I had.
Well,
I can't remember the date, but I remember Feynman giving a talk enthusiastically about parton.
Yeah.
So could you clarify a bit?
Yeah, it was right after he said, you know, I'll look into it, that he started to work on partons. That's right. That was part of his.
And Yang had a sort of parton model, but they used to fight about what these entities were.
Yeah, and he called them partons. He didn't call them quarks because he didn't know if they were quarks. He just thought they were particles in it. And eventually he decided that partons were quarks. His line of thinking was, I think he did two things in parallel. One, he was working on partons, and the other he was working on photoproduction. And the photoproduction convinced him that there were quarks. And then once he thought there were quarks, then he identified them with partons.
Stefan?
From your current perspective today, how do you feel about the fact that because you didn't know anything, you were sent to experiment with it in the synchrotron?
Well, I think it was very good advice. I couldn't have done this if I wouldn't have been trained as an experimentalist. I worked with Alvin Tollerstrup, who was a fantastic guy. I mean, he just wouldn't put up with any crap. And he really, knew what a measurement meant and was and how you do it. So I recommend working in experimental physics, although I don't know if I'd recommend working in experimental particle physics. I think you don't have, it was great. I could run this experiment. It was a basic experiment. I could look for CP violation, one individual working with, there was one professor, 2 postdocs, and 2 students.
Good old times.
But they exist elsewhere.
Any other questions before we let her go? If not, let's thank the speaker.